So hey everyone, I'd like to talk to you guys a little bit today about a project that we've been working on in the data sciences team for managing workflows, sort of handling Ensemble jobs where we want to operate in a more throughput computing mode and get a lot of jobs through in spite of the queuing policies at LCF, which are geared more towards capability jobs. So first I'll talk a little bit about what kinds of scenarios you may find Balsam useful in, to give a little bit of context, and give a sort of a high-level overview of what exactly is Balsam, where do the components run, and why might you want to use them, maybe some strengths and weaknesses of this approach. And sort of the heart of the talk is a walkthrough on Theta, so hopefully once that gets uploaded, you can follow along. There's a module on Theta that you can load and hopefully try some of these examples to set up a Balsam workflow. And then I'll go into a few more involved examples, sort of from real-world workflows that we've seen in ADSP, and sort of what common patterns are for getting a large number of jobs into Balsam and then monitoring their execution over time. And then a couple other features I'll sort of just highlight briefly in setting up dependencies and defining a DAG or directed acyclic graph of your jobs to manage data flow and perhaps monitor the workflows in real time to kill and create jobs at runtime. So first of all, I know that the term workflow itself may be a little fuzzy. And all I really mean here is your strategy for executing the applications that you have. So once your development and performance tuning is done and you have some number of jobs to run, your workflow is just simply the means by which you go about that. And in some cases, you don't need anything fancy at all. If you could consume a certain amount of compute time with just a handful of jobs. So if you have 10 to 100 jobs, this is perfectly manageable with shell scripting and the GNU tools built in to Linux, and you may not need anything more. But in cases where the number of jobs gets huge, which is something we see commonly in these data-intensive projects, you may need to do some kind of parameter scans or perform simulations to generate, for example, your training data to build some models. In that case, sort of the constraints in the LCF computing environment can become cumbersome. And the goal of the workflow is to help you in this case and sort of facilitate scheduling and execution. So I'll first give sort of the quick and easy way. If you don't have too many jobs to run overall, you can set up Ensemble jobs on Theta in a Cobalt shell script. And the way to do this is to simply background AP runs, which I believe Chris mentioned in the first talk of the workshop. So with a little delay between app runs, you should be able to sustain up to 1,000 concurrent app runs per job. And of course, you can change directories and pass different arguments or environment variables per run as necessary. And this is probably the quickest and easiest way to get throughput on machines like Theta, where we have sort of stringent queuing policies that favor large jobs. So, for instance, you're given the minimum node count of 128 on the default queues, and a maximum number of queue jobs at 20. If you have a huge number of jobs to run, you really want to be using this kind of approach to increase your throughput. But the problem with this approach is it needs a lot of help if you're going to scale to large numbers of jobs. So if you go up to a huge number of application runs, or you start having dependencies between steps in your workflow, there are a number of challenges. So first of all, how can we maintain good resource utilization? We would like to be able to take out a big block of nodes and hours and just keep them busy. But the previous example sort of launches everything up front and then waits. So we would have to add logic to monitor busy and idle nodes and dispatch work as they becomes available. And then it can become sort of cumbersome to track which jobs finished, which ones timed out or failed. And this involves sort of an iterative process of parsing outputs, regrouping for the next run, and sort of there's a lot of human in the loop work here to keep your workflow running. And so there's really two solutions here. You can build your own tools, so you can write more sophisticated shell scripts or use Python, or you can invest in a system that has already, sort of tried to abstract some of this on your behalf. So that's probably one of the biggest reasons a workflow manager can help you, is that it can ideally make your large computational campaign very organized. The ones I'll be talking about can help you automate the actual scheduling of jobs so that you're not too concerned with corralling which tasks run in which Cobalt jobs. They should keep concurrency high and sustain good utilization of the resources that you're sort of paying for, and they should be robust with respect to application level faults. So if something goes wrong or if a job doesn't have enough time to finish, these things should be easy to track down and take appropriate action to continue. And a lot of workflow managers, and in Balsam specifically, there is a notion of provenance, which is that you're recording metadata about your workflow as it runs. So we get a history of when did jobs execute, if errors occurred, were they logged, and then we can use this to look at sort of statistics of how well are we using the machine, what's been our throughput over time. So from a very bird's eye level view, Balsam consists of three components here. There's a database that you set up and run on your behalf, and a Balsam service that runs optionally on a login node. And then there's a launcher that runs on the back end to dispatch your work. So the database holds a table which we call a Balsam job table, which has one entry for each application run that you're interested in. So you basically have a number of ways, command line interfaces or Python APIs, to interact with this database and sort of define your workflow there. And then the launcher is the pilot process that runs inside a Cobalt job. So once your Theta nodes are reserved, it's going to run and pull tasks from the database. And this thing basically takes the job of your normal shell scripts, issuing app run or MPI run to send work to the back end. And then optionally, we can use, we can dispatch launchers ourselves, or we can use a service that will actually package jobs and size overall Cobalt submissions to run launchers for us. I think one of the big strengths of this approach is that there's a very low barrier to entry, and you have absolutely no modification necessary of user code. Because everything is running on isolated resources, there's no need to relink or modify MPI codes. It's easy to insert and query jobs from the command line or Python interface. And it's tested, sort of, the components have been designed to work well under large numbers of jobs. So we've had a recent ADSP workflow with over 1 million jobs in the database, and it seems to work well on Theta under those conditions. And then we also sort of have been, we've been actively researching what are good ways, what are best practices to run big ensembles on Theta. So if you're following this approach, we sort of can help you understand limitations and what we've encountered in running ensemble jobs on Theta. And related to that, resource isolation is that sort of confers a lot of fault tolerance to the workflow. So even fatal errors in a job, seg faults in tasks will not take the rest of the workflow down. Failed jobs are just replaced by the next available work, and this keeps utilization pretty high, and errors are generally logged for sort of quick identification of what went wrong. And it really supports as much concurrency as you want. You could have multiple launchers running in separate COBOL jobs and consuming work from the same database across any number of nodes. And there's really no restriction on whether you're running mixtures of serial or MPI jobs here. So we can compare this. I think it may help to understand Balsam a little bit by comparison to a few other tools. So CRAM is a tool it's not really correct to call it a workflow manager, but it is a very powerful approach to run large ensemble jobs. And this is really nothing but a library that you link against your application, and you sort of specify a large number of instances to run in a CRAM file. And here you can pass working directories, arguments, environment variables for each run. And under the hood, it's basically splitting up the global MPI communicator into a bunch of subcommunicators, fooling them into thinking they're sort of the global one. And in this way, you can run a huge number of MPI tasks under one COBOL job. And this is like one app run on Theta. So an advantage here is that there's absolutely no strain on the mom node, whereas we have limits, process count limits on Theta if we're launching one AP run for each MPI task. The drawbacks here are that this is sort of a static definition of the catalog of jobs to run, and so everything starts at the beginning of the job, and the job will take as long as the slowest run. So there's no real opportunity for load balancing, as I understand it. And because everything is running under one sort of monolithic MPI runtime, it's not the most fault-tolerant approach. And then there are more sort of proper workflow systems. I grouped Swift and Parcel here together because these are both sort of systems that allow you to express a workflow as code. So Swift has a sort of a C-like syntax and is a data flow language, and Parcel is a Python library that gives you some decorators to annotate code with sort of data flow constructs and control basically the order of execution of tasks. These are very powerful ways to sort of encode a workflow. If you can describe it this way, it's very concise. And then the backend is the Swifty backend that both Swift and Parcel can sort of compile to, is running an MPI runtime, which is very high performance and has sort of proven scalability on LCF systems. But one of the biggest challenges here is when you have a large number of MPI jobs that you want to run within an ensemble, and there's sort of a lot of issues with doing MPI inside MPI because there's basically some development overhead to get one application working and exposing an entry point with a communicator, subcommunicator that it can run under and so on. And again, this is sort of coupling things together, which comes at the cost of reduced fault tolerance. So with that, I'd like to sort of just show you where we can get started with Balsam on Theta. So there's some documentation available on the LCF site. It's a little bit behind some of the current features, but this is undergoing an update right now, so we should have up-to-date docs here soon. But there is a module available on Theta, which was tested yesterday. So if you load Balsam module, you'll find that it will complain if you don't have Python 3.6 or newer loaded. So An easy way to do that is to just pull another module like CreatePython, and then the Balsam command line should show you all the available subcommands that you can use to control the system. So to get started, we use this command Balsam init to generate a new database directory and sort of populate it with the necessary subdirectories. You should see this message after running Balsam init, and it will actually create a new folder for you at the specified path. And then for context switching, we use sort of a source activate command borrowed from a Conda package manager. So you would specify a name or path to one of your Balsam databases, and this will check on whether a server is running against that database, and if not, start one, and set your environment variables so that you can begin working against a particular database. So here's sort of just a really quick example of filling the database with a few jobs and watching them run from the command line. We use this Balsam app command to register new applications. So in this case, we're just using the shell built-in echo and assigning this name to it. And then for each instance, for each run of this application, we define a Balsam job. So this command has a large number of parameters you can use to control how a job is run. But this is sort of a very minimal command line where we give a job a name, a workflow tag. Most importantly, we reference the application that was defined previously, and then we give command line arguments to this application. And after running this command, you'll sort of see a confirmation with sort of showing defaults of the various fields in a Balsam job, and all of these are directly settable from the command line that you just saw. So for instance, you can provide different numbers of nodes or ranks per node if the job is going to run with MPI. And then at the end of this thing, you should see a summary of what command actually gets run, and Balsam will generate a working directory inside of your database directory here, in which each task runs. So we can use the shell to add a bunch of these, and then the Balsam ls command is what lets us list the tasks in the database. So you should see something like this, and basically the status of a run is tracked under the state column. And so when you first create jobs, they're under the created field. And as Balsam processes jobs, executes them, they'll sort of go through a flow from state to state, and that will be recorded in the sort of provenance data. And one of the easiest ways to actually run is with this shortcut submit launch provided by Balsam, and this will actually execute qsub on your behalf. So these arguments look exactly like the arguments to qsub. The one difference here being that you specify a job mode, and I'll talk a little bit about that in a second. But at the end, you should see a confirmation that the submit went okay. And after some time, if you rerun Balsam ls, you'll see that all of the tasks are now finished. And then if you run this history command, so ls with the ---- hist, you'll see the metadata I was talking about. So in this case, the Balsam launcher is skipping. We didn't really specify any actions to run before the execution of the job, but we see these tags nonetheless for pre-processing, starting and ending the run. And here, there are lots of optional constructs for data movement, running scripts before and after a run, error handling, and so on. And all the output from these jobs ends up in the database directory that was created. So under this data folder, you'll find a bunch of subdirectories which are grouped according to the workflow tag that you gave. And then job working directories are sort of auto-generated in this way. So you should find your outputs here. And this can be overridden too if you want to enforce a different working directory for your job. And then here's another example that will sort of show how Balsam runs under failed tasks and give an indication of the states that you'll see when tasks fail. So here's just a small simulated script, which is actually using MPI. So I'm also going to illustrate running with few ranks here. So we define Balsam application here that to run that task. I didn't show, but that was, I think, running with like 6 ranks. So Balsam treats that as an MPI application. And then you'll see that the failed status is recorded here. And when we run the history subcommand, we can actually see a log. So it will capture some of the trace back here. So filtering for failed jobs in this way, sort of a convenient, quick way to pull all the logs of failed jobs and try to get a handle on what's going wrong. And then finally, there are command lines to modify tasks that exist in the database. So this modify subcommand takes job ID, an attribute, and a value to set that field to. So for instance, if a job is failed and you fixed the problem, you can modify the state to this restart ready, and then the job will run again in an existing launcher or in the next job that runs. And then you can also use this Python API, which is based in the Django ORM. So this Balsam job object kind of inherits all the functionality of a Django models. And there's a lot of documentation on what you can do with those. But basically, we could do some pretty expressive queries for, in this case, searching for all jobs under 128 nodes containing the name test that are finished. And then suppose we want to run those again, we can just do a batch update to the same restart ready state. So this is kind of a more convenient way to manipulate the database if you have more than a couple jobs to control. And then finally, let me talk a little bit about how this works when we have a large number of jobs to run. So we have this molecular crystals ADSP, which is, I think, renewed for second year now. And one of the challenges a couple months ago was that the PI basically came to us and said they need a huge number of DFT calculations done on various polymorphs of these molecular crystal structures. The goal being to produce some large training data set. And then this obviously is not going to be very pleasant to do from the command line. So I think this is a good illustration of a really common motif of how do you get all the work into Balsam. And probably the easiest way to populate the database is using this API. So it's very easy to use existing tools in Python. For instance, in this case, we're crawling some directory of input files, finding matching ones for each input file that we find. We're creating a Balsam job object here with this helper, and then using this bulk create functionality to insert jobs into the database. And then this is really nothing but defining a Balsam job in this way. And again, all of these keyword arguments match the options that are available from the command line. And then to actually run, once you have a large number of jobs in your database, again, the submit launch shortcut is very helpful. But this is doing nothing but submitting basically a template shell script on your behalf. So you can write your own script or modify the template, as I'll show on the next page. In this mode, basically, each launcher is going to consume as much work as it can. These are cooperating through an application level lock to basically avoid collisions or working on the same tasks. And then alternatively, when you're using the Balsam service, that is actually assigning tasks to launcher jobs so that there's a little bit more coordination planned ahead of time there. So if you look in your Balsam settings.json, this is automatically created when you start using Balsam in your home directory. There are a couple files worth mentioning. One is this job template that I mentioned. So on Theta, you get sort of a default Cobalt job scripts template. And then if you're using the service, then this queuing policy comes into play. So first I'll mention the template. There's a lot that goes in the middle, but basically at the top it looks like your ordinary Cobalt job file. And in the middle, we set up some environment variables and we run this Balsam launcher command. And so this here is what actually operates on the mom node, like I showed towards the beginning of the talk. And so you can use this outside of a template. You can very well write your own scripts that invoke Balsam launcher after pointing at the right database. And then when you're using the service, the queue policy file looks a little bit like this. So this is where you can control which queues you're submitting to, maximum number of jobs to have in a queue at a given time, and sort of constraints on the windows of job sizes. So you can specify node ranges and ranges of time that Balsam will try to pack your tasks into. And then as the workflow is running, you want to monitor progress. So here we have this by states flag to LS. This is a very useful way to categorize jobs. You can also pass a limit to not flood your screen, and you end up with something like this. So this is a view from that molecular crystals workflow, and you can see it's very sort of easy to follow in real time how many jobs are running at any given moment, which ones are completely finished or still waiting to run, and so on. Yeah, so now I'll go a little bit into some features that you can use to add dependencies and dynamic attributes to your workflow. So this is just a really brief example, but if you have some DAG describing the data flow in your job, it's very easy to use this add dependency function in the DAG module of Balsam. And so in this case, we create sort of this diamond pattern of jobs A, B, C, and D, and E. And then we create dependencies from parent to child between A, B, A, C, A, D, and then finally dependencies from each of those to the final step. So this is all doable from the command line as well, but this kind of pattern is probably easier to reproduce from a Python script. And then the DAG module also has lots of conveniences for traversing job graphs, doing queries, and then also kind of providing some convenience that is context aware. So when a job runs or one of the pre or post-processing scripts attached to the job runs, Balsam exports a few special environment variables to that job so that when you import this DAG module, you can access the current job referring to what's being processed there. And this is a really useful way to sort of write dynamic workflows. And that, for instance, in a post-processing step, you could inspect the current job, check the state, which may be failed or successful, and then you can parse outputs and modify the database in response. So according to your own logic. And this is sort of a programmatic way of building a dynamic workflow. And one of the features that I think is kind of unique with Balsam is the ability to kill jobs at runtime. So you can query jobs and then pass them into this kill function. and this will mark them for termination, and the launcher is continually checking for these things. So this signal will actually propagate to running launcher jobs, and they will be replaced in near real time with the next tasks in your workflow. Yeah, so finally I'll talk, before the last example, I'll mention that we found a really common pattern in sort of these more tightly coupled workflows where we have one task actually running under Balsam and producing the majority of the work. For instance, in global search methods for hyperparameter optimization, we'll have a search task that is producing a number of model training and evaluation jobs, and we want to run these asynchronously and then check on their progress and update the search state this way. So this is where maybe a more tightly coupled approach makes sense, as you would see with a dedicated workflow scripting language. But with Balsam, we provide some modules. So for instance, the async provides some constructs that look a lot like the futures that you find sort of in the Python standard library. And this kind of abstracts the need to pull the database repeatedly in a job that is monitoring other jobs. So basically, if we are building a large collection of jobs, we can wrap them in this future task construct, providing a callback to take some action and return a result from the job. So then we can use this wait to pull on futures either asynchronously or synchronously in blocking until some set of tasks are done. And then basically, we can run things that way. So the HyperOpt workflow that we've been working on, called DeepHyper, is sort of making use of these concepts. So this project is sort of spearheaded by Prasanna in MCS, who was talking about a number of issues yesterday with machine learning. And one of the challenges there is for really large deep neural nets, we want to find sort of optimal hyperparameters like batch size, learning rate, and even tuning categorical parameters like which kind of loss function or optimizer to use. So DeepHyper is something with a release sort of forthcoming. We're looking at sort of a best way to provide this to users on Theta, but right now it contains sort of a collection of ML benchmarks. So these are various deep learning or toy models with associated training data, and each one has sort of an associated hyperparameter search problem. So this is a definition of the search space and sort of bounds on the variables that we're searching over. And then DeepHyper provides a variety of optimizers that can basically bridge to any one of these benchmarks. These use sort of an abstraction for the actual process, the training and validation of models. And this allows us to tie DeepHyper in with Balsam or multiprocessing if that's more appropriate for testing on your laptop. So I just want to point out quickly that in integrating DeepHyper with Balsam, we made some optimizations to database access and the polling that I showed previously with the futures to sort of try to minimize the bottleneck that Balsam poses in this workflow. So this is sort of just showing results from a random search over 8 hyperparameters for this recurrent neural network benchmark. And we see in going from 128 to 1,024 nodes, throughput increases almost, I think, by 7.6x. So this is 96% efficiency in scaling up. And this is just the sheer number of hyperparameters that are evaluated and for which the network is built and trained and objective function returned to DeepHyper. So for a system like this, random search is really a very fast algorithm, so it lets us probe whether or not Balsam layer is sort of creating a bottleneck here. And this is sort of good news, at least up to the test we've done on a quarter of Theta. And then something else that you get for free with Balsam is the execution metadata I was talking about. And there are convenience functions to pull metadata and construct graphs like this. So this is sort of from a single run on 64 Cooley nodes, actually. We get something like the number of running jobs at any given moment in time. And so this fraction out of the total number of workers that you have is basically your utilization. And so you see in this case, we're basically pegged at 100% utilization throughout the run. And then we can look at things like throughput here. So this is something that's kind of convenient and easily accessible from the Python API with Balsam. And that's about it. So in summary, if you're interested, if you have a large number of jobs to run and you're looking for some organizational strategy here, Balsam can be a good way to do that. And you have the sort of backing and lessons learned by ADSP project teams doing this on Theta. I think we're most happy with the fault tolerance and provenance that we get out of running these workflows. It really makes post-processing and managing a workflow over the course of days a little bit easier. And then there are a lot of tools under development, like I showed you, for building task graphs and running dynamic workflows. And hopefully that these can satisfy more complex use cases if you have them. And so, yeah, with that, I'll take any questions. Yes, that's a good question. So the question was, you may be using Intel Python in a different version, maybe Python 2, but I was showing that you need to load Cray Python 3.6, which the Cray is actually not a requirement here, but you do need 3.6 that's just for running the Balsam components. So the service and the launchers are running under 3.6, but the executables therein are completely isolated processes. So that those could be any flavor of Balsam or Python. Yeah. Yeah. So the question was, if you have a 400 node job, which is I/O bound, maybe by stressing metadata, and you decide that you can tolerate another 200 nodes, can you scale out to 600 nodes in total? And yeah, the way the approach Balsam takes is that you basically would just submit another launcher job. So you would have 400 nodes running. That's what Cobalt gives you. And if you want 200 more, we're constrained by the same queuing policy as everyone else. But that 200 node job can come online at the same time, and they will cooperate through locks in the database to pull the same stuff. So originally, it was built in a very modular way. That's still there. There are scheduler plugins. So you can interface to other kinds of schedulers. There's really only a few places where the scheduler plugin is relevant here. So it shouldn't be very difficult to swap. But you can actually run, from what I talked about, it's really just that shortcut for submitting a job. Once you have Balsam running, you can run the launcher in other environments. Yes, this is a user application. So it's submitting, if you're using the service, it's submitting jobs to Cobalt on your behalf, and it's parallelizing things on your behalf. And no, there is a central database, but it belongs to you. It's private to you. We're using Postgres here. So we started with giving users options, and we had an SQLite backend, and we found that concurrency is very buggy with SQLite. It may have something to do with the network file system and the way POSIX file locking works there. So Postgres it's definitely a more heavyweight, but it has really superior performance, and it works really well when you have lots of launchers, sort of all clients to the database at the same time. And this Balsam init that I showed you sort of completely encapsulates the process of creating, administering the database. So you shouldn't ever have to look at SQL if you're using Balsam, unless you really want to. Yes, so there is a repository. We have a sort of a development repo and another one mirrored in a public location. That's a little bit behind. But if you're using the module, you're reading the source code anyway, so you can read it on Theta. Yes, it's a little bit behind. So the documentation that's on the ALCF website right now, some of the, for the most part, the examples in defining like a DAG and running that will still work. But I think the command line interface was overhauled quite a bit. So what you'll see in these slides, which should be available for download soon, is going to be a lot more up to date. Yes, there's an internal GitLab repo, and we need some. So as the documentation is updated, we will mirror it to a public repo as well. Right. So by default, if you don't pass any additional flags to Balsam submit launch, the launcher is going to consume everything from the database. But you can add a filter. So there's a workflow filter tag. And that's another use of, providing that field. And so you can submit jobs to only run specific kinds of workflows, maybe one job per DAG or however you want to categorize your work. It has to go to the same place, right? Because you're using local storage. Yeah. So the question was, is there some node locality-aware logic in Balsam to sort of co-locate dependent jobs in the same place to reduce data movement? That is there are several people that have requested that feature, and it's not in Balsam yet. So that's something we will work on. Right as it exists now, basically they assume everything that a job needs is going to be accessible from the working directory of its parent jobs, which are then, naturally in a shared location. That being said, if you have a couple of really tightly coupled steps that need to use RAM disk or SSD, it might make the most sense to just group those, call that one job, and let them run together. So we have there are other experts in the data sciences group that are working in parallel I/O and sort of strategies for data movement in general. So I think that's going to become a really important part of workflows that are so, data intensive. Right now, there's something like that. If you're, tuning striping, you would have to manage this yourself at the application level. So there's no support in Balsam for that kind of control.
Misha, it was good that you compared Balsam with some of the other workflows. There's like a lot of materials in chemistry people have asked me about.
Fireworks?
Fireworks, but also more a question about Balsam. I guess there's some. It's really kind of domain science agnostics, but or is anybody working on like modules that might kind of facilitate common things like their material scientists might be interested in?
Yeah, that's a great question. So I've sort of spoken with Alvaro about that several times of developing. Well, I come from a computational chemistry, so we were talking about specifically, chemistry-specific modules that you maybe are using Balsam DAG functionality to sort of make it really easy to template common, tasks in chemistry. But I think that the tools are there for that. We haven't really built out much of that functionality yet, but there are features to, for instance, define a blueprint DAG once and then create copies of it with different inputs. And so I would imagine it's just a question of getting all the applications in place and getting your blueprints down, and then packaging those into something that people can use to run